In section 3, we can look at another way to convey this information about the accuracy of the statistics that we get. So suppose that we have an approximate sampling distribution for p hat. Okay. We can think of a confidence interval. Which is an interval that you think includes the value of the population characteristics. So we just talked about that in a sense, where we took that 0.64 and subtracted 0.04 and added 0.04 to see where we thought P really was. And any confidence interval also has a confidence level. A confidence level means how confident are you with your success rate of the method that you used. So it's associated with the confidence interval is the success rate of the method used to construct that interval. Okay. So if we look at this, we can look at this simulation of a normal curve, and if we have 1.96 here, I'm sorry, negative 1.96 and 1.96 here, and remember P is the mean of that distribution. This is 1.96 standard deviations lower than the mean, right? 1.96 standard deviations below the mean. And this one would be 1.96 standard deviations above the mean. Okay. Now, if we look at the standard error, the standard error means that P really could fall anywhere from this value minus this number and this value plus this number. So if we look at this, we know that the green line represents 1.96 standard deviations below the mean. We're going to use this to create an interval of values to estimate P. So consider the picture here. Okay. If P really was right here, then all of our values within 1.9 standard deviations below and 1.96 standard deviations above the mean are on this line right here that I've just drawn. It's that red line. But now, when we take a sample, we are not necessarily going to get the actual value of P. We're going to get an estimate. So if we think of this estimate right here and we go 1 standard deviation below and 1 standard deviation above, not all of the values are going to be within that range of 1.96 standard deviations of the actual population proportion. Same thing if we take another, some of them will be too low, some of them will be out here, right? But if we take another sample and we get a different population proportion, or sample proportion, and we go 1.96 standard deviations below that, 1.96 standard deviations above it, not all of the values are going to necessarily fall within this area right here, 1.96 standard deviations of the actual value. So we could get an interval that doesn't include P, right? So suppose that we look right here. Uh-oh, I've got something that looks freaky. Okay, let's go back here. Here, looks much better now. Okay, so suppose we get a p hat that actually lies out here, because we could get a p hat that is not in this margin of error at all. And so since this is, because we have 95% of all of the data points would fall in here, 5% could fall outside of that interval. So using this method of calculation, the confidence interval will not include P, the actual population value, 5% of the time. So this number was created because we wanted 95% of the time. You know, we wanted our value to fall, the actual value of P to fall in our confidence interval 95% of the time. So that number can be changed, and if you use a larger number, then you'll get a larger interval, which means that you have more successes, more than 95%, and less failures that percent of the time. If you use a smaller number, then the interval will become smaller and you'll have more failures. So it depends on what the experiment is or what you're trying to show, and what the statistician decides is of the interval that they want to use, if they want a smaller interval or a larger interval. And for right now, we're just going to stick with 95%. Okay, so based on what we were just looking at, we are able to say that for 95% of all random samples, the estimation error, which is the difference between the value of the sample proportion and the value of the population proportion, will be less than the margin of error. And what that means is that we can create this confidence interval, which is our calculated sample proportion minus the margin of error, and then our calculated sample proportion plus the margin of error. And so sometimes it's written this way: p hat plus or minus the margin of error, instead of writing it as an interval. Okay. So again, when we have certain conditions that are met, we are able to use this, right? Let's review. We know that the sample has to be random, or has to be a representative sample of the population. We have to have a large enough sample size so that we can expect 10 successes and at least 10 failures. And when those conditions are met, a 25% confidence interval for the population proportion looks like this. Okay. So this formula corresponds to a confidence level of 95% because of that number right there. And just so you recognize that the confidence level associated with the confidence interval is the success rate of the method used to construct the interval. So what does this mean? Okay, it means that you can be 95% confident that the actual value of the population proportion is included in the calculated interval. Okay, we can never say that we are 100% confident that that actual value is included. There's always a margin of error. Okay, so suppose remember that also our confidence is in the method used. It's in the method, not in any particular interval. So how we say this is really important. We are 95% confident that the actual value of the population proportion is included in that interval. You know, we don't want to say that it is, because we know that our method is only going to be right 95% of the time. So we can't say that we're 95% sure that this is the population proportion when we come up with a p-hat. It's not that we're confident that that's the value of p. We're confident that our interval includes the value 95% of the time. Okay. So suppose that we wanted to calculate a 90% confidence interval or a 99% confidence interval. Remember that from our empirical rule, if we wanted the central area to have 90%, then we would find those z-values to be negative 1.645 or positive 1.645. So to calculate this confidence interval, a 90% confidence interval, it's going to be done the exact same way as a 95% confidence interval, but we're just going to change this number from 1.96 to 1.645. And we'll have p hat times 1 minus p hat all over n. If we wanted to calculate a 99% confidence interval, exactly the same thing would happen. We'd take the calculated sample probability or sample proportion. We would subtract, in this case, 2.58 times p hat, square root of p hat times 1 minus p hat all over n, and get our interval that way. Now remember, if we want to get more of the area, then our interval is going to be bigger. If we have a smaller amount of area, then our interval is going to be our interval will be smaller. And it's that those critical values, 2.58, 1.645, or 1.96, that determine our confidence level and how wide our confidence interval will be. Now we're going to look at putting kind of all of this together, all that we've looked at from chapter 7 on. Okay. So if we have a large sample confidence interval for P, that, remember, is appropriate when the following conditions are met. We have a random sample, or the sample is representative of a population. And I know you're getting tired of me saying this, but I will keep repeating it, because without these conditions, we can't do any of the stuff that we're trying to learn how to do. Okay. Secondly, the sample size has to be large enough. We have to have a sample that we expect to include at least 10 successes or 10 failures. When we meet those conditions, we can calculate p hat, calculate the error, margin of error, and create a confidence interval. And that's the generic formula for creating a confidence interval, right? This z value that we calculate depends on how confident we want to be. And that's our standard error. So really what you're doing is you're taking your statistic, you're adding or subtracting the critical value times the standard error of that statistic. And that's going to be, even when we're not working with just proportions, this generic formula is going to work for any confidence interval we're going to create. Okay, so now let's go back and think about the concepts that we learned in chapter 7 to look at a statistical problem and make some analysis from it. So suppose we have 1,100 drivers that were surveyed. 990 admitted to careless or aggressive driving during the previous 6 months. Assuming that it is reasonable to regard the sample of 1,100 as representative of the population of drivers, we want to compute a 90% confidence interval to estimate P, the proportion of all drivers who have engaged in careless or aggressive driving in the last 6 months. So, we first answer our 4 key questions. Okay. The question type. What type of question is this? This is an estimation problem, right? We are trying to estimate a proportion, the proportion of all drivers who have engaged in careless or aggressive driving in the last 6 months. This study type is a survey. It's just sample data. We're not conducting any experiment. What type of data is it? Well, it's only one variable, yes or no. Did they engage in careless driving? And because you're answering yes or no, it's categorical data. And the number of samples or treatments, well, they just took one big sample. It doesn't matter that there are 1,100 drivers. It's one sample that consists of 1,100 drivers. So, what does this mean? The method we'll use is a large sample confidence interval for a population proportion. For a large sample population proportion. Now, how do we know that? Well, we know that population proportion because we haven't learned anything else, right? But if you go back and you look on page 116, then you can see how answering the 4 key questions as estimation, sample data, one variable, one categorical variable, and one sample size tells us that's what we want to do. So let's go back and look at that right now. Right here we had an estimation problem from sample. The study type was sample data, univariate categorical with one sample, and that tells us that we are looking for one sample z confidence interval for a proportion. Okay, which of course is chapter 9, which is what we're looking at right now. But again, you want to have this information. This would be a great thing to put on your form so that you would know which test you're going to use depending on how you answer these questions. Okay, so let's go back and actually start the 5-step process for the estimation problem now. Okay, so where we left off. Because this is an estimation problem, we do the 5-step process for estimation. Okay. So let me go back. First of all, step 1, we have to come up with the estimate, right? So we say that the estimate is the proportion of drivers who have engaged in careless or aggressive driving in the last 6 months. So step 2 is the method. So the method is determined because of the 4 questions above. So we say because of our 4 answers above, we'll consider a confidence interval for a population proportion. All right. So now we are going to check our conditions. Remember that once we decide what method we want to use, we have to have our assumptions met or we can't use it. So first we have to say, is this a representative population or was it a random sample? And if you look back, it says, assuming that it is reasonable to regard this sample as representative of the population of drivers. So yes, it is. And now we want to know, is this big enough? So we had 1,100 surveyed and 990 admitted to careless or aggressive driving. So 990 out of 1,100 is actually our proportion, our sample proportion. Yes. And so 2 is the sample big enough? And so really, when we're finding n times p, what that really is the number of successes. Well, how many successes were there? There were 990, because it told us 990 said yes, they were aggressive over the last 6 months. And if 990 out of 1100 said yes, then that means that 110 had to have said no, which is also bigger than 10. So how we would calculate this mathematically, though, is 1100 is n, and then 990 out of 1100, oh, not 1,000, 1100, is our proportion of success, and that gave us 990. That is definitely bigger than 10. And then n times 1 minus p, 1100 times 1 minus p is what's going to add up to give from 990 over 1100 to give us 1. So that's just going to be 110 over 1100. And if you did that on your calculator with decimals, 990 over 1100 is 0.9. So what would 1 minus 0.9 be? It would be 0.1, which is the same thing as 110 over 1100. And that ends up being 110, which is also greater than 10. So our conditions are met. Now we'll actually calculate that interval. So 0.9 was our sample proportion. Actually, and if we want this as a 90% confidence interval, then we want our z-score, our z-number, to be 1.645. And then this would be times the square root of 0.9 times 0.1 all over 1100. So if we calculate that, we get a confidence interval of 0.9 minus that number is going to be 0.885, and 0.9 plus that number is going to be 0.915. So there's our calculated confidence interval. And now we need to do two things. We need to communicate our results by interpreting the confidence interval and interpreting the confidence level. And I know this is a pain, but you need to write out exactly like how I write this out. Okay? Because you need to be able to explain what this means. So we would say, assuming that the sample is representative of the population, of drivers, you can be about 90% confident that the actual proportion of drivers who engaged in careless or aggressive driving in the past 6 months is somewhere between 0.885 and 0.915. Okay. 88.5% of the population to 91.5% of the population. That's a lot. That's a very high percentage. Okay. So now we want to interpret the confidence level. So we would say that the method used to construct this interval estimate, because it is an estimate, is successful in capturing the actual value of the population proportion about 90% of the time. Okay, so I have some typos here because I had originally done this. I was going to do a 95% confidence interval, but I decided to do a 90, so you'd have a little bit of practice using a different number. We want to be careful. The 90% confidence interval for P calculated was this. And it is tempting to say that there's a probability of 95% that P is between these two numbers. But you don't make a chance statement or a statement about probability concerning the value of P. That's not what that confidence interval refers to. The 90% refers to the percentage of all possible random samples that would result in an interval that includes P. So it's actually not talking about the value of P at all. It's talking about these intervals that you would get from random samples where you calculated P hat. So what it means is if you take a sample after sample after sample from the population and use each one separately to calculate a 90% interval, in the long run, 90% of these intervals would capture P. It doesn't mean that that specific one you have captured P. Okay, so I know it's a little strange to be thinking about it that way, but it's really important that you understand this. So what this is this diagram right here actually is, it shows basically a chart. These were all the P's that were found. Okay, and this was done with a 95% confidence interval. Okay, but these were all the intervals that were they just calculated sample after sample after sample and found these lines represent the confidence intervals, and P is actually the population characteristic, and these asterisk intervals right here are the ones that were calculated but did not include the actual value of P. Okay? And that's what that sentence is talking about, that we're the method that is used, we expect that the interval calculated would include the value of P 90% of the time or 95% of the time, or so it doesn't mean that P is It's not a probability about P at all. So the three things that affect the width of a confidence interval, right? The confidence level, and the higher the confidence level, the wider the interval. If you're 95% confident, you're going to have a much wider interval than if you're 50% confident. Right? The next thing that affects it is the sample size. The larger the sample size, the narrower the interval. Okay? Because your standard error goes down with a larger sample size. And remember that the closer p hat is to 1/2, to 0.5, then the wider the interval is going to be, because the closer p hat gets to 0.5, the bigger the error is going to be. Okay? So sometimes people ask questions, what happens if the conditions of the sample size is not met? Right? Because we have to check it, and if those conditions are not met, we cannot use this method for creating a confidence interval. There is an alternative for finding a confidence interval with a small sample size, where we can't expect to get 10 successes, or at least 10, and at least 10 failures. There's an activity in section 9.2 that explains this if you're interested in it, but we are not going to be doing it in this class. Okay, we're going to be focusing on the statistics that can be done when those conditions are met. And if you're interested in more in-depth, then you really want to take a more in-depth statistics course. All right, so we still have a little bit more to go in chapter 4 or in chapter 9, but I hope that you're starting to get an idea of how to create a confidence interval and how to use the 4 questions and the 5-step method in order to do that.